Hello, Geometry Gurus. We are starting Unit 5, and we are going to be working with right triangles in this unit. And what you remember about a right triangle, or what you learned about right triangles before, is Pythagorean theorem, a squared plus b squared equals c squared. So in using the Pythagorean theorem in our geometry applications, we are still going to use a squared plus b squared equals c squared and do some basic algebra stuff, which means we need to review and know how to work with radicals, simplifying radicals, operations with radicals, and that's also going to lead us to some of the new geometry stuff we know about, well, not we know, that I know about right triangles that eventually you will learn. All right, so what I'm going to do is ask you to pause the video, and I want you to write down as many perfect squares as you can remember, just numbers that are perfect squares. Okay, so pause the video, write out as many as you can, and then come back. So there's 1 through, oh, I should have added 0. 0 squared is 0. Technically, that's a perfect square. Anyways, that's 0 through 21. So you can see how you did. What kind of an exponent makes a variable a perfect square? That's obviously an exponent of 2. That's what it means to square something. If we had perfect cubes, it would be an exponent of 3. Perfect quadruples, it would be an exponent of 4. But to square something means multiply it times itself 2 times. So a square makes a perfect square, exponent of 2. So for non-negative real numbers, a and b, you can take the product of the square root of two numbers and separate it into the two individual radicals, and that's what we're going to do to simplify our radicals. Similar to simplifying or reducing a fraction, it's the same value, it just looks different. We can do that with radicals. What we need to do is find the largest perfect square factor of the given number. Oops. So in other words, if I look at all the different pairs of numbers that multiply to be 108, I may have multiple perfect squares that are in that list that are multiples of 108, but I want the largest possible option. If I don't take the largest possible option first, then I have to go through this process several times in order to reduce the value completely. It's kind of like if you were to take, if you had the fraction 50 over 100, you could reduce it by 10, making it 5 over 10, and then reduce it again by 5, making it 1 over 2. So it took a couple steps to get down to the final reduced version. But if I went to the beginning and then reduced by 50 right off the bat, I would get to the same result with fewer steps. Same thing is going to happen with each of these radicals. If I use the largest perfect square factor, the first time I do it, I only have to go through this process once, and I'll get the simplified answer right away. So the question is, how do I find the largest perfect square that is a factor of the given number? Well, that's why we have technology. So on the calculator, what you can do, go get your calculator, pause the video if you need to, go find your calculator. But what we can do is go to the graph. So once your calculator is turned on, we're going to go to the graph. If you see a tab function, then you can type in our number that's under the radical divided by x. So we had 108 divided by x is what I would type in for this particular question. If you don't see that tab function, may be missing, just hit tab. If yours happens to say something else like relation, we can fix that by going to menu, option 3, and then option 1, make it a function. Then it'll put it to f of x. But once you have your number that's under the radical divided by x, you'll hit enter, and it doesn't matter if there's a picture there or not. Then we'll hit Control T and look for a table of values. Control T on your calculator brings up the table of values. Control T will make the table go away so you don't see it anymore. Control T brings the table back. So now what I'm looking at here, the left side is the x values. The right side is the y values. In the y column, on the right side of your table, you are looking for the first perfect square that you can find. 108 is not a perfect square. 54 is not a perfect square. 36 is a perfect square. So that means 36 is the largest perfect square factor of 108. So now back over to what we're doing with our notes. That means I can take this square root of 108 and rewrite it because it's the same thing as saying 3 times 36. And if it's the same as 3 times 36, then with the product, I can separate the two radicals. And then I know that the square root of 36 comes out to be exactly 6. The square root of 3 is irrational, which means it stays in the radical. That is simplified completely. Now we just do it again. This time we are looking for the largest perfect square factor of 48. So back over to here. Control T takes the table away. If I want to start from scratch, menu, 1, 4, enter, clears out all the old stuff. Tab gets me where I can type in my new number, 48 divided by x. Enter. But I want the table, so Control T. Now find the largest perfect square. The first perfect square that I see is 16 times 3. So back over to my paper. This will be 16 times 3, which is radical 16, radical 3. Square root of 16 is the perfect square of 4. Radical 3 is irrational, stays a radical 3. 200. You might just be able to do this one quickly without having to go to the calculator. Also, you might want to go to the calculator to make sure that you're not doing it too quickly. But for 200, I can do the square root of 100 times the square root of 2, which makes us 10, radical 2. Okay, pause the video, do letter D, come back when you're done. So what you should have done is 25 times 3, which is 5 radical 3. With letter E, when we have a number, a coefficient in front of the radical, we are going to keep that number, but not apply it until after we simplify the radical. This technically means 4 times the square root of 180. So we have to simplify the square root of 180 first. Then when we're done, we'll multiply it times 4. So we need the largest perfect square that is a factor of 180. Control T gets the table out of the way. Menu 1, 4, enter. Enter. 1, 4, enter. It clears the old stuff out of the way. Tab, so I can type in my new number of 180 divided by x. And then Control T brings my table back. Largest perfect square, right there. 36 times 5. So 36 and 5. 36 is a perfect square. Then 4 times 6. So here's where the 4 comes back into play. Now that I've simplified the 180, I'm going to take the 6 that came from the simplification and multiply it times the 4 that was in front of the problem all along. So this becomes 24 radical 5. So why don't you pause this, try F, and then we'll see how you did. So hopefully you were able to simplify the 112 into 7 times 16. Then the square root of 16 is the perfect square, so that becomes 4 radical 7. And then 4 times negative 28 be negative 28 radical 7. All right, so pause the video and try G. So hopefully you actually pause the video and tried it on your own. Notice that sometimes I put the perfect square first, sometimes I write the perfect square second. When you have the numbers written inside the radicals, it doesn't matter which one you write first, but once you take out the perfect square, that goes in front of the radical. we would write something with a variable, 3x, 4x, 12x, 12y. The number comes before the letter. We put the numbers in front of the radicals. Similar process. Okay, so for 147, you're going to do your largest perfect square that is a factor of 147. Pause the video, find it, and come back. But it's going to be 49 times 3, which gives us 7 radical 3. All right, so that's your basic simplification. Now what we need to do is be able to do some operations with these things. So just like with the multiplication on this page, multiplying two numbers underneath the radical can be separated into the product of their separate square roots. Same thing happens with division. If you take a fraction and square root that fraction, you can either square root the whole fraction or square root each individual part. So we can separate it. Now, which one do we do? It all depends on the numbers you have. So if you look at example A, if you recognize the fact that you have two perfect squares in your fraction, then you can separate it and take the square root of each one on its own. So if you recognize your perfect squares, then you can separate your fraction into the two separate radicals and then just do the square root of each piece separately. If they're already separated and they're not perfect squares, it might be helpful to put them together so that you can divide first and then take the square root. And of course, there's some times where neither one of these is going to lead you to a perfect answer. But it's all about knowing the rules and being able to use them based on the situation that you have. So this one, if I did 75 divided by 3, I recognize that I would get a perfect square of 25, so I can just do that, so the final answer just simplifies to be 5. Okay, so what happens if we put exponents underneath the square root? Well, if I take the square root of a squared, I'm going to get back to a. That works for all real numbers. The square root undoes the exponent of 2, so the square root of a squared is back to a. So if we did the square root of 35 squared, we get 35. But be careful. Technically, what's happening is we are doing the exponents inside the radical first, and then after that taking the square root. So technically, this becomes negative 15 squared, which is 225. Then unsquare that, or square root that, back to 15, so we end up with a positive answer. Okay. Similarly, here, we're going to end up with negative 6 squared, which is 36, over 4 squared, which is 16. Then that will square root perfectly back into positive 6 over positive 4. If you're multiplying the parts and trying to figure out what's what the answer is, again, negative 2 squared turns into positive 4. 12 squared turns into 144. Because it's the product, there's two ways you could do this. You can multiply them together. So if you jumped on your calculator and did 144 times 4, then, excuse me, then you would get 576, which is a perfect square. The other option is you could have square rooted each one of these individually, which would give you 2 times 12, which is still 24. So you could do it either way. So what happens when we have other exponents other than 2? Well, there's two possibilities. Either the even exponent or the odd exponents. That's the only two choices for numbers when you're dealing with numbers. You either have an even number or an odd number. So, we're going to look at what to do with each one. Whoa. If our exponent is an even number, just divide it by 2. Divide the exponent by 2, and it gets written outside of your radical. So all even exponents are perfect squares. All even exponents are perfect squares. So if you look at our examples down here, 26 to the 10th, 10 is an even exponent, so you just divide the exponent by 2. Next one, x to the 30th. 30 is an even number, so you divide the exponent by 2. 17 is not an even number, 21 is not even. Let's see what else. Well, I guess that's the only one. Those are the only ones that are even. But that's as easy as it can get. If you have an even number for the exponent, divide it by 2. So what happens if it's not an even number? Well, if it's not an even number, we have something else to do. So if it's not an even number, we're still going to divide by 2. But the issue is going to be, since we're dealing with an odd number, when we divide by 2, we're going to have a remainder. So we're going to have a remainder of 0.5. When that happens, that means our exponent was not a perfect square. So very similar to what we had when we started this, we're going to have a piece left over in the radical that's not part of a perfect square, and we will have a piece that comes out of the radical that was from the part that was a perfect square. So it's going to have a very similar kind of result. So here's what we do. We take the exponent, divide it by 2. So if we do 17 divided by 2, you guys know what we get? Do you? I don't hear you. Okay, so you get 8.5 or 8.5. So here's what we're seeing. The 8, the number, the digits in front of the decimal, that's our perfect square portion. The 0.5 means you have one piece still left over. Okay, so that's how it looks. Kind of weird with numbers, but we'll do it again with variables on the bottom. Let me explain real quick, maybe this will help, why this 0.5 goes back into the radical. In math, this is something you'll do more in Algebra 2 next year, the square root can be written as an exponent, and it would be an exponent of 1/2. So if you go to your calculator and you do your regular calculator screen, if I do the square root of 25, we know that I'm going to get 5. If I do 25 to an exponent of 1/2, it does the same thing. If I do 25 with an exponent of 0.5, which is the decimal version of 1/2, it does the square root. So an exponent of 1/2 means to take the square root of something. Now, if I have something like x to the 8th underneath the square root box, then technically this is taking x to the 8th to the 1/2 power. You learned in algebra, when you have power to a power, you're supposed to multiply the exponents together. Half of 8 is 4, so take half of the exponent. The issue is, when I have an odd number here, like 17, and I do x to the 17th to the 1/2, I'm supposed to multiply the exponents the same way I did the above example. That gives me an exponent of 8.5. That is the same thing as saying 8.5. That is the same thing as saying x to the 8th, x to the 1/2. And if we go back to where we started, x to the 8th times x to the 1/2 would be x to the 8th times the square root of x, because x to the 1/2 is the square root of x. So x to the 1/2 is the square root of x. So whatever happens to be inside the radical, in this case it's a 2, not an x, when I do the exponent divided by 2, the number in front of the decimal is the exponent I use out front. The 0.5 that's left over always leaves one of those values in the radical. In this case, it's 2. So let's look at our second example, or actually, letter D. Next example. The square root of 25 is a perfect square. That comes out. Square root of 21 can be split into x to the 20th is what I meant to write. X to the 20th and x to the 1st. Adding the exponents would add up to 21. 20 is the largest even number that's smaller than 21. Half of this exponent means we get x to the 10th, x to the first. 1 is an odd number, stays like that. That's a little bit different way of doing it than what I did here. But if I did it the other way, 21 divided by 2 is 10.5. There's the 10. There's the radical x that represents the 0.5. Okay? So that's how we do it. Letter E. The 4 gets dealt with at the end. Here we have to simplify the 18. And we can do the k to the 7th separately. 18 splits into 9 times 2, so it becomes 4 times 3 radical 2. And then if you take 7 and divide it by 2, you get k to the 3.5. Your exponent is now 3.5. 4 times 3 is 12. The k to the 3.5 means that an exponent of 3 gets used on the k, and that goes in front of our radical. The 2 that was left over from the 18 goes back inside. Remember that the extra decimal 3.5, the 0.5 part, means there's still a k in my radical. So k to the 3, and then radical k is the 0.5 portion of that term. All right, a lot to take in. So we have negative 7. We're going to simplify the 175. So if you need to go to your calculator, then do that. But it's going to be 25 times 7 is 175. And then if I do 25 divided by 2, we're going to get 12.5. That's the exponent. So now when we organize our answer, the square root of 25 is positive 5. The 12 portion of my m is the exponent on the outside piece. Inside my radical, I still have the irrational number 7 and the extra m to show that the original exponent on m was not an even number. Final answer, when you multiply the negative 7 times the 5, is negative 35, m to the 12th, radical 7m. All simplified, all in one. So why don't you try the next two? Pause the video, try the next two, and then we'll see how you do. All right, so the 3n, just like in the previous example, is going to be dealt with at the end. Our 98 comes from 49 times 2. And if we take half of 11, it's 5.5. So then this becomes 7n to the 5th. 7 coming from the square root of 49. N to the 5th coming from the 5 that's in front of the decimal. And then in the radical, we still have the 2, that was the irrational number, and an extra n because of the 0.5. Now do that times 3n. So 3 times 7 is the 21. Add the exponents on the n to make it n to the 6th, and then radical 2n, finish it off. And letter H. I think you should try this one on your own, and then come back and I'll do it with you for you. So as you try this, you may have found that 37 has no perfect square factor. It is a prime number, so that means that will stay as is. So I only have to deal with the h. So that means if I take my exponent of 73 and divide it by 2, I get h to the 36.5, 36.5. So the 36 part is the outside exponent, in the 0.5 part means I have an h still inside the radical. And then when you multiply variables, you add the exponents together, so it's h to the 48th radical 37h. All right, that's as far as we're going to take lesson 1 for today. What I want you to do is go to the problem set, and in the problem set, you're not going to do everything. You're going to do numbers 1 through 9, and then on number 14, you can do letters D, E, F, G, H, I. Based on what we just talked about, you have enough information on your paper and hopefully in your noggin to do those questions. And then if you want to go ahead and do radical video 2, or part 2 for lesson 1, or you can wait till tomorrow, because that's tomorrow's assignment is to do part 2 of lesson 1. So be good, stay safe, watch this video as often as you want. I know it's ridiculously entertaining, but I'll talk to you soon. Bye.